Assalamu alaikum. My name is Mobeen Malik, and the lab I'm going to perform in front of you today is the verification of De Morgan's laws and implementation of Boolean functions through logic gates. So, the first De Morgan's law states that x plus y whole complement is equal to x complement into y complement. X and y being two inputs, and the second law is just an inverse which states that x into y whole complement is equal to x complement plus y complement. These laws, as you may realize, are just distributive laws of multiplication over addition and addition over multiplication. So if we see, these are their truth tables. For the first law, which is x plus y whole complement is equal to x complement plus y complement. This is the left hand side of the equation and this is the right hand side of the equation. Now if x and y have 0 as their inputs, the left side of the equation is 1. Also the right side of the equation is 1. And for all the other values, again they both have the same values, which means the left hand side and right hand side are equal, but only through truth tables for now. Let's implement it on Proteus and show how they are actually equal. This circuit in front of you is the implementation of the first De Morgan law. These components represent the left hand side of the equation, while these components represent the right side of the equation. X plus y. Here the first input is x and this is the second input y. They come to a NOR gate which then gives out x plus y complement. Now if x and y are both turned off, you can see that both of LEDs are blinking, which means that at the same input they are also having the same output. Now if I turn one of them on, then you can see that LEDs have turned off, but they have done it simultaneously, which means that these both sides of the equation are actually equal. For the next law, it states that the product of x and y and their whole complement is equal to the x complement plus y complement. The products represent the AND function and the sums represent the OR function. And now you can see that if we have zeros at x and y, the left hand side of the equation gives out 1 and the right hand side of the equation also gives 1. Same follows for the 1 at y or 1 at x, where they both have 1s at their outputs. But if both of them are turned 1, then we have nothing at the output. So if we see it on the Proteus, this is the circuit we have in front of us. Now you can see this is the left hand side of the equation and this is the right hand side of the equation as I have labeled. So if I turn one of them on, there is no effect on the LEDs. But if I turn both of them on, then the LEDs at both outputs turn off, which means that both sides are equal. Now I will show you the implementation of some other Boolean functions through their truth tables. Now these are some of the other Boolean functions for which we have to build a circuit and verify their truth table. The first equation or the Boolean function is x plus y into z. Now for this function to be 1, either this has to be 1 or this whole part y into z has to be 1. And for y into z to be 1, both of y and z have to be 1. So if we see from this truth table, y and z here are 1. So we have 1 at the output, while the value of x is 0. And for all the other conditions where the value of x is 1, we have a 1 at the output no matter what the value of y and z is. For this demonstration, this is the Proteus circuit, and this OR gate basically represents the x plus y into z. And what is y into z? This AND gate. Y into z is represented by this AND gate. This is the input y, this is the input z, and this is the LED which will show if we have an output or not. So if we run this circuit, you can see as all three of these are turned off, we have no output. So if I turn the X on, you can see that there is an output. So if I turn the X off and turn Y or Z on, you can see that there is no output. To get an output because of Y and Z, both of Y and Z have to be turned on to get an output at the LED. The next Boolean expression for which we are going to verify the truth table is A complement B plus C complement D, which means A complement and B are C complement and D. As you can realize that this means that either this value has to be 1 or this value has to be 1. And for these values to be 1, the complement value has to be 0, so it gives out a 1 actually, and the B or the second value has to be 1. You can see the truth table for this expression right here. If we analyze all the ones at the output, for example this one comes because of this C being 0 and D being 1. When C is 0, its complement value gives 1, and the D1 gives out a total of 1 from this expression, regardless of what the values of A and B are. These four ones come because of the one value of B and the one value of A complement, regardless of what the value of C and D is. This one comes because of D being 1 and C being 0. This comes because of the same reason again. Now let's go to the demonstration part in Proteus. This is the circuit which we will use to demonstrate the Boolean expression. Now this is the input A, this is the input B, this is the input C, and this is the input D. Now we have no output right now because all of the inputs are 0, but actually this 0 gives a 1 right here as there is a NOT gate attached. Same goes for this one. Now if I turn B on, which means that there is a 1 here and 1 here, which makes the AND gate give out a 1, and this turns on the LED. Same goes for here. If I turn the C on, the LED turns on, but if I turn the D on, this means that there is a 0 here and there will be no output. So this verifies the truth table for this Boolean expression. Now this is the last Boolean expression which we are going to implement. This reads as A complement and B complement, or C complement and D complement. This implies that either this value has to be 1 or this value has to be 1. And for any one of these values to be 1, C and D, or A and B, both of them should have the value 0. As you can see, if we analyze all the ones in this expression, these first 5 ones are because C is 0 but D is 1, which means that this value is 0, but both A and B are 0, which gives a 1 at this side. And for this one, both C and D are 0, which gives a 1 on this side. For this one, these C and D are 0, which gives a 1 on this side. And for the last one, C and D are 0 again, which gives a 1 on this side. This is the Proteus circuit that is used to verify the truth table for the given expression A complement B complement plus C complement and D complement. As all 4 of the inputs right now are open or 0, this means that all inputs after the NOT gates are 1s and give a 1 at the output. To give a 0 at the output, one of the inputs on both sides has to be 1, which gives the complement value of 0, giving the output as 0. This can be verified for the other 2 outputs as well, like this too. And now if we turn both of the inputs off at one side but leave the other one on, it still gives a 1. This was the demonstration of Boolean expressions using the gates. I hope you've learned a thing or two. Thank you very much. Allah Hafiz.